What is going on, guys? Mirko with the WordTech here, and today I'm doing another C++ tutorial. However, we are going to go back to doing binary search trees. So I haven't done binary search trees in a while, or I haven't done any coding videos in a while, probably because I'm not actually taking very many coding classes this term, so I don't really have kind of like the whole want to do these. But however, there are some people that requested to do them, so I will, and I think it's just good practice anyways to me to look back at them. So we are going to be doing another binary search tree tutorial. If we could remember last time what we did for the binary search tree, we just did some basic functions like delete all, count nodes, find the largest node, find the smallest node. Now those are like the most basic things, how to traverse back and forth on a tree, something you'll see kind of on a more intro level class, when we are still going to be doing more intro level classes. But I think the things I'm going to be talking about today are going to be a lot more important than just finding the largest, counting the nodes, and deleting all of them, which are really important. So guys, today what we're going to just be doing is we're going to be working with subtrees, and we're going to be working with the in-order successor. So the whole entire part, like I said on my last tutorial for a binary subtree, or a binary search tree, sorry, is going to be placing your values that have a numerical value, or placing your data that has a numerical value somewhere in the tree that makes it easier to find. That's pretty much the whole entire reason of even doing a binary search tree. So for example, think about this. I have 4 people. I have Dan, Bob, Joe, and David. Dan has $5, Bob has $10, Joe has $20, and Dave has $20 or $25. So if we want to see who has the most amount of money, what we can do is we can place whoever has the middle amount of the value as the root. So for example, whoever had the $10, we're going to have 10 as the root. And then whoever had the $5, that would be its left subchild, which would be the left subtree. So 5 would be left of 10, and then we have 20 and 25, which would be that 20 is to the right and 25 is to the right of 25. Sorry, F20, and I'll have a diagram of that. So basically, it allows us to place values so we know exactly where they are within the tree, because the whole point of it is, if you're looking for a specific value and you know it's going to be bigger than root itself, then there's no reason to go to the left subtree, because everything on the left subtree is always going to be smaller than root. So typically, if you're only looking for something that's bigger than root, search on the right side. If you're searching for something that's smaller than root, search on the left side. As you guys can see, we did that there. For smallest, we only went to the left subtree, and then for the largest, we only needed to go to the right subtree. So what we're going to do is we're just going to do something just for a counting the left subtree. So this is going to bring on more advanced. This function that I'm going to be writing right now will be nothing really advanced, but it's going to bring more advanced conceptual concepts that you can do with binary search tree. So as normal, we're going to have a case that's just going to be if not root. If we don't have anything, then we want to get out of there, or else we're going to dereference a null pointer and we're going to cause a segmentation fault. The next thing that we're going to want to do is we're going to have another check, and we're just going to check if we have one pointer. So if not root left and not root arrow right. Oh, can't type. That means we are only going to have one node in the whole entire tree, so we return 1. Now the next thing that we're going to do, this is actually going to look pretty similar. So we're going to do the normal counting function that we have down here, except we're going to have a little twist to it. So you're probably thinking this is right now as the function sits, it is just going to count the whole entire subtree, and we can pretty much prove that just by looking at the count nodes. So if we did left sub, which is our function name, and then root arrow left, go to the left first, plus left sub root arrow right. And then just to let you guys know, I'm still working with the same setup as last time. I just have a struct that's a node, and then after that I just have normal functions that are in the whole entire space. So going on, as you guys can see, this is just pretty much the same function. We have nothing new here, just the same function. However, when we call it in main, it is going to be different. So you guys can already see how it's called in main. But what we're going to do is, we know we have an integer return type. So what we're just going to do is, we're going to just call it int left equals left sub. And then now here, I think is going to be the most important part. So the most important part about this is, we want to count the left subtree. So you don't want to just do this. If you do this, this basically means you already just wrote the count function. However, what we want to do is, we want to call it on root's left subtree, or the node that's directly to the left of root, which means if we call it to the left of root, that means we're going to just call it specifically on the root's left, which is a whole nother tree, which means we're only calling it on that section. It'll never call on the right side, because by the time we get up to it, it's going to recursively return, and then we're just going to pop off from the stack frame and we're going to be done. So by the time we do that, we're going to call it on the left side, and then we're going to go all the way through down and count everything. So let's test it. When we compile, right there, a.out. So as you guys can see, we actually didn't see out anything. That's probably a problem, and I don't know what main is called. CS299. So then, of course, we're not going to see anything if we don't see out. See out left and line. Boom. Oops. So we compile and run that, and then as you guys can see, our starting root is going to be 86 at level 1, and then directly to its left and right we have 100 and we have 21. So that means 21 is going to be to the left, which would mean since 21 is directly to the left of 86, that means to its right are going to be 35, and to the right of 35 is going to be 70. As you guys can see, we have root starting at 86. If we count the left subtree, which would be all the numbers to the left, we have 3. We can rerun that again, and as you guys can see, we start off at 21, which would be right here, and then we'll count all the way back, and then we have 3. So guys, that's going to be for counting just the left subtree. Now what we're going to be doing is, we're going to do something called working with the in-order successor. So I think the most important thing to understand about binary search trees is what the in-order successor is, or the IOS. And I can do that later on. I can explain to you guys why the in-order successor is so important. So basically, if you want to do any kind of removal with the in-order successor, it's basically, if you want to do any kind of removal at all with the binary search tree, you're going to need something called the in-order successor. And an in-order successor would basically mean what is the next largest number. So for example, if 20 is going to be your root, the next largest number that's going to keep the tree balanced and not completely shift the tree is going to be something that's larger than 20, for example, which would be 21. So what we would do is we go into root, and then the in-order successor is always going to be 1 to the right all the way to the left of root. 100% always that's going to be. So that's going to be pretty easy, right? So the only thing we need to do is, we're just going to check if not root, we're going to return 0. So guys, after we have our basic check case of if not root, we're going to have another check, which is going to be if not root arrow left. And basically what root arrow left is going to be, it's going to be our check if we are all the way to the left of the subtree, of the right subtree. So if we are all the way to the left of the subtree, what we're going to do is we're going to return, if I can spell, return root arrow data, which would mean that we are going to return the data that is at that current node. If we're not there yet, we specifically just want to go to the left. We never want to go to the right when we are looking for the in-order successor. So root arrow left. Boom. So we're going to keep on going all the way to the left. Once we get all the way to the left and then we can't go any farther, then we're going to just call it on root. We're going to return root arrow data and grab that data. So when we go over, you'll see that we have if not root, and then if not root arrow left, which means that we're all the way to the left of the data structure, and then we have iOS return arrow left, which means that we keep on traversing. Now, we always know that we are always going to be looking on the right subtree because we want the next largest item, and the largest item is always going to be one to the right all the way to the left. So since we only want to work on the right subtree, guys, we're going to have another variable. I'm just going to keep it to the left. We're going to call iOS, the function that we made to get the in-order successor. But since we are only going to be working with the right subtree, we're going to call it on root right because we want to just go one to the right all the way to the left. So what this will do, we're at root right now. We'll go one to the right because of this call right here. And then after that, we're going to keep on recursively returning down to the left until we reach if not root arrow data. So if we were to call that, you will see that our root is 72 and then our next greatest value is going to be 81. So I think that's going to be the important part of learning about binary search trees, are what is going to be the important value, such as like the iOS, which I think is going to be the most important thing that you guys really grasp. If you want to do any kind of removal function, any kind of remove odd, remove multiple, remove something in the middle of a tree or something, you always need to know what the in-order successor is because you need to rebalance the tree, or unless you're just going to lose that entire tree. So guys, I hope you guys just enjoyed this video. These are still some of the basics of a binary search tree. I can go over more. I can go more over advanced algorithms such as like deleting odds, deleting evens. It's going to be using the same exact thing. However, I think for those would just be its own separate video. But guys, if you guys enjoyed the video, please leave a thumbs up below and let me know if you guys would like to see some more. That is all for you guys today, and I'll see you guys in the next one.